So the last presentation is on optimized bridge preservation strategies by Richard Cantin of Simco Technologies.
Good afternoon, everyone. Glad to be here today. I'm going to talk to you about optimized preservation strategy. So globally, it's an approach, and we're talking about preservation of bridges. So what to think about when we want to optimize repairs or even the construction of a new structure. So what to consider and what to take into account. So I'm going to talk about the limitations of the current approaches, the durability analysis, what is a durability analysis also, and I'll discuss the proposed approach as well. So traditionally, inspections are done by rating bridges. So this is an example. Ratings can be different across agencies, but the idea is to inspect on a regular basis and then assess a rating on an element or a structure, and as the rating decreases or increases depending on the system, we come to a point where an intervention is required. And at that point, the damage is done. So even it can be a given percentage of the lamination, cracking, or every organization has its own criteria. So in all cases, it's a reactive intervention. So we can't intervene before we see the defect. What we'd like to do would be to kind of see things coming before the damage is done in order to optimize the repairs. So these inspection approaches have some limitations, and the main one is that we don't see what's inside the concrete just by visual inspection. So in some cases NDT is performed, that's better. Sampling can be performed as well, that's even better. But if we just rely on visual inspection, we don't see what's going on inside the concrete, and we don't know what to expect and when to expect it. And also, well, what we have is reactive interventions, and we often apply standard procedure. So the procedure is not adapted to the deterioration that is observed, so its extent or its root cause. So if we keep doing the same thing for any type of deterioration that we see, it might work or it might not, depending on if we are lucky enough to address the cause of the problem. And recently there was a survey that's been performed. Well, I say recently, it's about 10 years ago, but the picture was not looking really good in the US and in Europe regarding concrete repairs. So the percentage was roughly 50% of success for concrete repairs, and the reason is that, as I was mentioning, doing or constantly the same type of repair, regardless of the extent or cause of deterioration, is like flipping a coin. So sometimes it works, sometimes it doesn't. And the causes of the repair failures were mostly inappropriate design, poor installation, or inadequate materials. So all these things relate to the design of concrete repairs. And these numbers come from a study that's been performed in Europe. And what is interesting in those numbers is that depending on what you're repairing, the success rate can be very different. So it's much easier to repair something that occurs right from the start. So a construction defect, for example, can be more efficiently repaired by a patch than a damage that is caused by something that is within the concrete. For example, ASR, the success rate of interventions is very low because the problem is within the concrete. So just patching concrete that is affected by ASR doesn't do anything good, because expansion will go on and damage will reappear solely after the repairs are done. Now a few words about the durability analysis. So if we want to evaluate the root cause of the problem and fix it with the appropriate repair, we need to perform a durability analysis. So what is durability first? It's the ability of concrete or a material to resist weathering action, chemical attack, abrasion, or other conditions in service. So that's the definition of ACI, the basic definition. ACI 365 adds another line to it, and it specifies maintain serviceability over a specified time or service life. So we have the material, we have the environment that interact together, and we want this interaction to give us a good performance over a specified period of time. So there's a notion of service life here that can apply to repairs or new structures. We may want to get 10 years, 25 years, 40 years out of a repair, or even longer in the case of new structures. So we need to be aware of what material we have, what is the environment, and how we can design these structures. What affects the service life of a structure? Well, I just mentioned that. So it's the interaction of the design, the geometry, the materials, the environment, and the maintenance. So for example, the design can be the type of steel that is used, the cover that is used as well. It can be, materials can be the type of concrete, what we put in the concrete if we use corrosion inhibitors, if a coating, a protective coating is applied. So these things all interact together and affect the service life. And of course the environment, and as we just discussed, the maintenance. So if the bridge is cleaned, if the water evacuation is maintained, or if the drains are clogged, this will also affect the service life of a structure. So one large part of the durability analysis, and when it comes to evaluating the durability of repairs and concrete structures, and trying to make repairs last as long as possible and build structures that will last as long as possible, is to evaluate what are the potential degradation mechanisms that can affect the concrete. So what the concrete is exposed to. And you can see on the left that there are two different categories, but that relate both to problems that are within the concrete. To the far left, you have internal degradation mechanisms. So these are reactions that occur within the concrete. The problem is there, it's triggered by the environment, but it's not a surface problem. So if you do a surface repair for something that is deeper inside the concrete, it's not going to work. The second column from the left, it's another type of problem that is within the concrete, but that can be triggered by the environment. But in that case, it's mainly a surface problem. So this can be erosion, freeze-thaw, or shrinkage. So it can affect the surface of the concrete, it can be repaired, it can stop. So we have some control on these, or more control on these degradation mechanisms. The third column is something that has less to do with the concrete and more to do with the environment. So there's not necessarily a problem within the concrete, so there are no defective aggregates or there's no weakness, but the concrete is exposed to very severe conditions, and contaminants can enter within the concrete and generate either corrosion, chemical attacks, and so on. So to solve these degradation mechanisms or to the problems that are related to them, then we have to act on the environment rather than on the concrete itself. So depending on the degradation mechanism, there's a different approach to use for repairs or for designing a new structure. And these approaches, the approach involves either avoiding what we can avoid right from the start, or monitoring the evolution or predicting how fast the degradation will occur. So things that can be avoided, for example, is freezing and thawing damage with a good concrete mix design, damage caused by volumetric change, so we can minimize the shrinkage potential, the thermal deformation. We can act on the ASR as well. So there are a lot of things that can be done at the design stage, and that either we can avoid the degradation or mitigate it. There are other kinds of degradation that evolve with time. So now we're talking about external contamination. So for example, chlorides penetrate inside the concrete at a given rate, and even if we have the best concrete in the world, it will penetrate more slowly than in bad concrete, but it does progress with time, and in that case, it's good to figure out how fast it goes to know when problems can be expected. Same thing with chemical degradation as well. So for extreme industrial environments, we can determine how fast degradation will occur, but we know it will occur. It can be completely avoided. So that's the approach in general terms. Now the methodology to use this approach or to implement this approach, the objectives, it's not to completely do new things. So like I said earlier, a lot of agencies already, well, inspections are performed, so we can use these results. NDT is performed, we can use also these results. Past inspection reports, all the procedures or the methods that are currently in use can be leveraged to at least increase the accuracy of predictions or improve the durability of the repairs that are done on bridges or on any other structures. And in the end, well, it reduces the cost of overall maintenance, and also it can optimize the inspection schedule and the resources, the budget and the human resources that are attributed for the inspection and maintenance of bridges. So the strategy can be described in 3 different steps. The first one is to evaluate the current condition. The second one is we determine where we are. If we have to repair a bridge, we must know what's the current condition. Then we must determine where we're going after that condition. So when damage is expected to occur in the as-built or the current condition or in any repaired condition. And then if we know that, we can evaluate if we need to repair, when, and how. So this is basically how it works. So it can be more detailed in different steps. So I can mention we need to evaluate past inspection records, past testing reports. Also, another important step is field work. So this can be performed by anyone that is affected to the maintenance of the bridge, but we need the visual inspection. In most cases, we already have it. We need also, in certain cases, core extraction, and strategically located cores to evaluate the state of contamination of the bridge or the state of degradation, the extent of degradation, to evaluate the extent of repairs. And the other thing, NDE can be done also at this stage to document, for example, where the steel is located. So if you have a map of the concrete cover, you can evaluate when chlorides will reach that depth as a function of time. So you know exactly, or you have a good idea of where damage will occur on the bridge and the size of those repairs and when to expect them. Another step is concrete characterization. So we have to determine a few properties of the concrete if we want to predict or determine how things evolved in the past and predict in the future how it will continue to evolve. We also need to, as I just mentioned, to evaluate the current state of contamination and degradation. So this is done by testing. And in the end, we can come up with a repair plan and a rigid roll service life evaluation that is based on actual data. And I forgot to mention also that this approach what I'm talking about is not necessarily to be done on one bridge. So if you have different bridges for which the materials are similar, the exposure is similar, they've been built at the same time, we can do the approach as a global approach for a cluster of structures or a group of structures. So how it works in terms of durability design, it's a little bit like structural design. So most people are familiar with structural designs for which the given capacity is evaluated if the loads are, the resistance is higher than the load, so then we know we have the right capacity. We can calculate that. In terms of durability, it's about the same thing. So we have a geometry. Either it's a constraint on an existing structure, or we can design it for a new structure. So in that case, it would be, for example, the location, the cover depth, any areas where water accumulates. So this is the geometry. We need to work with that. Exposure conditions are the salt loading in the case of corrosion, but it can be also the temperature, humidity, all that relates to the environment and affects the concrete. And the resistance is basically the concrete properties. So in the case of chloride-induced corrosion, for example, we have bars that are located at a given distance from the surface. We have chlorides that want to enter the concrete. They have a given concentration at the concrete surface. This is an exposure condition. And then we have concrete that has a certain resistance to chloride ingress. All these three things together may be used to determine the time when the critical chloride content can be reached. The exposure conditions can be different for different elements, different zones of the concrete elements, so for the deck, the substructure. So ideally, we need to evaluate the different, or at least find the critical elements or the critical locations where damage is more likely to occur and be more frequent. So for example, we can evaluate differently the shoulders and the center lanes of a bridge, because the shoulders are where the damage occurs and the center lane not. So then we can come up with a repair program that's adapted to the actual conditions and not, we can overlay the entire bridge, but if we want to just repair where it's required to, we may locate where the damage is more likely to occur. And regarding the concrete itself, I just mentioned that we can act on different parameters to optimize the concrete mix, either a repair mix or a new mix, to influence the resistance to freeze-thaw, the resistance to cracking, volumetric change, chloride penetration, chemical attack. So if we know what the concrete is exposed to, we can act on the parameters that are the most likely to influence directly the durability and the service life of a given element. So I know that in many cases we use standard mixes, but the standard repair mix or the standard mix for a given structure is not necessarily the right one. So for example, I know that HPC is being used for bridge decks, but HPC may be good for some properties and may be bad for others. So depending, if we want to, for example, to have the best chloride resistance, we don't necessarily need to have the lowest water binder ratio. So we can have more flexible mixes with lower modulus that are less prone to cracking, but that still resist chloride ingress. So these things may be evaluated at the time a repair or a new structure is designed. I was talking about the current condition earlier. So this is the most important thing. So at least when we do a repair of a structure, or we design a structure and we can use information from sister or parent structures, we need to know the current condition. So in that case, I think the least is to or determine the depth of chloride contamination if we repair for corrosion, chloride-induced corrosion, or if we have ASR, for example, we need to determine the depth because ASR creates subparallel cracking. So you can't use standard repair procedures and say, for example, I will remove 3 inches of concrete or 1.5 inches without knowing if you're removing enough concrete or too much concrete, or if you're removing concrete at the right place. So you need to evaluate the condition, and in that case, chloride profiling might be a very good addition to the visual inspections. But if we go further and we have the concrete properties or, for example, the resistance to chloride ingress, then we can use the past history, considering the age of the structure, when it's been paved, if it's covered with asphalt, all that's been done in the past to recreate the actual chloride profile. And this gives us the exposure conditions. So maintaining these exposure conditions in the future, knowing the concrete properties, helps us to figure out what will occur in the future if we can reproduce what happened from the time of construction. So this approach, basically, what we do with that is that we can reproduce the gradation curves that we get by ratings, but we can also reproduce them by modeling. So if we can reproduce the past and predict the future, we have degradation curves like that, and in that case we can tell if we are more on the green curve or if you're on the green curve or the blue curve. But at any time we know when, or we can evaluate when the critical condition will be reached, and it helps predicting what will have to be done in the next few years, where it will have to be done, and how much it's going to cost, because all this can be used in the life cycle cost analysis, for example. So if you have those modeling or degradation curves, what you can do is that you can evaluate the current condition, something like that. If I do nothing, I have that gray curve here. I can do any kinds of repair. So a bad repair would be something like that. So I'm trying to extend the service life. I know I've not reached, so I'm trying to do preventive repairs, but I'm not doing anything good because the repair I'm implementing will not extend the service life of the structure. So I'm wasting money, I'm closing a bridge for nothing. So by means of modeling, we can evaluate that in advance. And we can also evaluate the impact, the cost versus performance of different options. So in that case, well, this curve here, blue curve here, would be something looking like cathodic protection. So I'm stabilizing the condition, and degradation occurs in the future, but at a later time. So I can gain on the service life this way, or there's another way to extend the service life. This would be, for example, replacing concrete. So then I'm restoring the condition close to the initial condition by replacing bad concrete with good concrete, but the degradation occurs at the same rate as well. So it shows that, and these methods have all costs that are associated to that, and you can time the interventions in the future as well. So it helps predicting what, or at least optimizing the budget that is available for the maintenance of a group of bridges or a major bridge, for example. And the strategy, as I mentioned, it has to take into account the budget. So it's not something that needs to be very expensive, but it's just a matter of knowing what we do and what we're looking at. So not doing the same thing without questioning what's the root cause of the degradation and how to address it. And in the end, we can come up with an optimized technique or material selection, and I would add also a maintenance schedule for a bridge. For example, as in the last presentation, when we were talking about washing bridge decks, one thing that can be done is to take chloride samples at different intervals, and then you can compare the effect of washing a bridge deck over a different given period of time. So in that case, this can be directly related to service life by means of modeling. So it's integrating all aspects of bridge of preservation strategies. So the benefits of this approach, I'm going fast on that, but it's basically it's an optimization of the budget and resources. So knowing what to do and when to do it helps to have a better use of the available money and staff to maintain a bridge. And I'm going to leave you on a few slides here. So if you have to remember something from that presentation today, reliable information for owners helps to better estimate how and when to intervene. So we need to know what's going on instead of just repairing blindly and the same way. Reliable information also helps to minimize closures, demolition, and interventions, because we can delay interventions and spread them a little bit more in time, ensure long-time durability at lower overall maintenance costs, and prioritize intervention, make best use of available budgets. What to remember as well is that if we determine the root cause of problems and anticipate future degradation, we can have optimized preservation of a bridge or a bridge element or any kind of structure. If we do standard repairs only based on visual assessment, there's an uncertain durability. It's a matter of luck. So if I remove 3 inches of concrete and it happens that I needed to remove that, that's good. If I needed to remove 4 inches, then chlorides may come back to the reinforcement and corrosion may go on a few years after the repair, for example. So that's something to keep in mind. Durability has to be considered when performing repairs and designing new structures, and this involves knowing the properties of the materials, knowing the exposure, so how these will react together, and also the design. So everything is linked together to get optimized repairs and optimized new service life for new structures. And last thing, testing for concrete properties, testing for exposure conditions, and I could add also a non-destructive testing like half cell or radar measurement for the cover depth. It helps to provide a good idea and a good evaluation of the current condition. That's the best thing to evaluate the current condition, and it's based on scientific principles. So it's not like guessing, it's really based on evidence and test results. So this gives a better assessment of the condition of a structure and helps optimize and the preservation of these structures.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.